Swayam Prabha. Digital India. Educated India.
Okay, last week we were talking about what really happens in a real flow. The theory that we have talked about so far refers to normal mode. That means we look at a single frequency and the corresponding wave numbers are selected by the eigenvalue search. In a natural flow, this is how you would see the trace. If you put a probe at a particular point, then this is how it would be as a function of time. These are at different locations from the leading edge of the plate. So, distance is growing in this direction. Corresponding Reynolds number based on current length goes on like this. What I mentioned last time also to you, that at the early stages signals are weak. That is why, for example, this signal has been magnified 4 times, this has been magnified 3 times, same here 3 times, 3 times. This one has been magnified 2 times, and last 3 are not magnified at all, to give you an idea what really happens. Few things become readily apparent, that they are not monochromatic, right. If it were so, you would have seen a single frequency event. So, it looks like a collection of many frequencies and they are mutually interacting. That is why you get wave packet like features of the flow. And what happens secondly is that when you go downstream, these increase in amplitude, all these disturbances show their amplitude increasing, and after a certain distance what you notice, the flow is characterized by very high frequency oscillations. These are very high frequency oscillations. So, this is one of the characteristic of all natural flows, right. Nonetheless, what happens here is that in this scenario, then if you want to validate the stability theory as it was done by these 2 gentlemen, Schuba and Skramstad, what you need to do is then remove any sort of trace of background disturbances, because what you are seeing is the effect of background disturbances. So, if you can create a wind tunnel for which the background disturbance is minimal and then you excite the flow at a particular frequency, then you should be able to check for all those waves that those have been predicted by the stability theory. And if you do that, this is the way that we said we follow a fixed frequency disturbance, that those are the rays starting off from the origin. On this side we have plotted the non-dimensional frequency, on this side we have plotted the Reynolds number or x. Okay. So, a constant frequency disturbance goes like this. It is only during its sojourn, during this unstable path given by this branch 1 and branch 2 of the neutral curve, that the amplitude increases, and that is what we have done here, because the relative growth rate is given by minus of alpha I, right. So, that if we integrate, we get A at any station x in terms of the amplitude at some reference station, and e to the power minus alpha I dx, starting from that reference station to the current station. So, what happens is for this flow, then what we could do is we can plot minus alpha I, that is the quantity of interest, and within the unstable band you would see that they will be amplified, right. And if I now perform that integral that is given in the exponent here, that is what we have done here, alpha I x dx, then we are going to see that amplitude is going to grow, and this is what we call as the n factor, right, for that particular fixed frequency. What one does, of course, is look at the behavior of different frequencies, and this also we explained that as the frequency increases, the flow becomes unstable at earlier location. Okay. However, it also comes out of the unstable path earlier. So, that is why you see it is growing and then it flattens off and then amplitude starts decaying. Whereas, if you look at the figure here, the lower frequencies are the ones which start off late, but once they are inside, they amplify to a significantly larger values. If we draw an envelope connecting the maxima of different frequencies, that is what we show here by the dotted line. That is what we call as the total amplification. Total amplification is the natural logarithm of a by a naught, the maximum value. So, in trying to represent the flow instability, then we start off with the critical point below which everything is stable, and from here on some high frequency starts becoming unstable, and you assume that in actual flow what happens is a kind of a interchangeably the disturbances migrate across frequency. How it is done, it is never explained, but this is empirically projected. That is why we really do pay heed to this capital N factor. Okay? And lots of experiments have been done, and people have tried to correlate this factor capital N, and they try to figure out whether the flow has undergone transition or not. For example, for a zero pressure gradient boundary layer, people have found out when this capital N takes a value of about 8 to 9, that is where you should expect a transition to occur. But let me sort of warn you up front that this is too empirical, because this does not tell you anything about A naught. Are we saying that irrespective of any tunnel or even in the same tunnel at different speed, are we going to see the same kind of behavior? That is something we will discuss. However, what we are next going to focus upon is what happens if we look at flows of different kind. Flows of different kind are characterized by, let us say, what the velocity distribution is in the inviscid part of the flow. So, that is what we are representing here by the Faulkner-Scan profile, right. The Faulkner-Scan profile is characterized by that external edge velocity distribution given by u e as equal to some constant k times x to the power n, and this is what is called as the Faulkner-Scan parameter. Okay. However, lots of work have been done, and Hartree specifically notes that what is of interest is this parameter called beta h, or the Hartree parameter, which is equal to 2 m divided by m plus 1. Okay. When of course, a boundary layer develops in a shear layer, then there are two thicknesses which we talked about are of interest. One is the displacement thickness delta star, the other is the momentum thickness, right. So, one basically gives you an estimate for mass displacement or defect due to the presence of the boundary layer, other one gives you the momentum deficit, right. So, h is a equally important parameter called the shape factor, and what you are seeing here is basically a velocity profile. So, what you are noticing here, you have plotted u by u e versus the height, right. Height also we have plotted y over delta star. So, you expect that the flow to reach close to value of 1 at delta star, but at the boundary layer thickness, which would be probably 2 or 3 times this delta star, that is where you would really get say 99.9% or so on and so forth. Now, as I said that we will characterize the flow profile by these two parameters beta h and a capital H, and that is what you are seeing. Please note that a 0 pressure gradient flow will correspond to m equal to 0, that is corresponding to beta h equal to 0, and that is what this is. See this top quantity beta h equal to 0. So, that is for your Blasius profile. Okay. The second last figure from the bottom, and corresponding shape factor for Blasius profile happens to be about 2.59. Above these two curves, we are seeing two more profiles for which beta h is negative and h is greater than the Blasius profile value. Beta h negative means the flow is decelerating, Okay. And if flow decelerates, what happens is you do get an inflection point. Remember, we talked about Rayleigh's theorem. We said that if we have an inflection point, those flows are unstable to inviscid mechanism. And you notice that depending on the value of beta h, you would have a different location where you are going to have the inflection point marked by the crosses here. This is one here and the other one is there. Okay. I asked you the question last time also, you can remember that for Blasius profile this point of inflection is actually on the surface, right, which is of no consequence because Rayleigh's theorem does not consider that flow to be unstable, right. Whereas, this last curve that is shown here for which beta h is equal to 1 corresponds to stagnation flow, right. So, if we are talking about flow past let us say an aerodynamic shape like this, so you will have a stagnation point. So, in the vicinity of the stagnation point, you will have a velocity profile for which beta h is equal to 1 and the shape factor is rather low. This topmost curve that you are noticing, that corresponds to beta h equal to minus 0.1988 and the h value is for 0.03. So, you can understand that if the flow is experiencing adverse pressure gradient, then you have the inflection point. So, those flows are inherently more unstable, and this is the situation where the flow is about to separate. That is what you are seeing. The behavior of the flow at the wall will give you some indication of whether the flow is attached or separating. Recall the Prandtl's condition that separation is indicated when the wall shear is equal to 0, right. So, what is wall shear? That is given by tau w, that we will write it as mu say d u e, well d u dy at y equal to 0, and that is what you are seeing in the last curve. This goes off tangentially up. So, this is a profile for incipient separation. Okay. Now, what does this really do? This is a qualitative description that we talked about. We can do the same thing. We can really draw the neutral curve for various kinds of velocity profile, and one standard reference neutral curve is this one corresponding to the Blasius profile, that is that beta h equal to 0, and then you notice that if I take the stagnation point profile, the neutral curve is like this. And please note, this is in a log scale. So, what you are seeing here, this is 10, this is 1000, this is 10 to the power 5. And what you notice that this value was, we earlier indicated, this is about 519 or so. That is the tip of this neutral curve for Blasier's profile. Look at the stagnation profile. That is very, very stable, because flow is stable up to such a large extent. In contrast, when you look at any adverse pressure gradient profile, for example, here if I take beta h equal to minus 0.1, what you notice that two features, the critical Reynolds number falls off significantly. Okay? So, this is roughly close to maybe 100 or so for this particular value. And the second thing is, you notice that for Blasier's profile, when it becomes unstable, it is due to a viscous mechanism, right? Because Rayleigh's theorem says that even if you look at the inviscid mechanism, it is stable. So, this is inherently a viscous mechanism. And what is interesting is, if I draw this curve far down, then the upper branch and the lower branch of the neutral curve for Blasier's profile will approach towards each other. That is one of the feature. That is what you see in all viscous flow instability. You see a sort of a limited region, and that region shrinks again, increasing with RE. In contrast, for an adverse pressure gradient, what you notice that this line is kind of parallel. So, it means what? That this is going to remain unstable. So, that is one of the indication that why adverse pressure gradient flows are not good from the point of view of instability and transition. And look at the value here for the incipient separation profile. There the neutral curve does not even close, it just remains open. So, it is going to remain unstable from a very low frequency to a very large frequency. Okay? This is of course an attribute of your linear theory, right. So, this basically gives you an idea of how to interpret flow instability from linear theory. This was done by Arnold and his group, and this picture reveals quite a few of the features that one would expect directly coming out from the linear theory. Recall, we plotted that capital N factor, which was nothing but maximum of ln A by A naught scanned over all possible frequencies. Now, what we have done here, we have plotted that n factor variation with RE for different values of shape factor. So, this is your Blasier's profile, h is equal to 2.59, and any value above this are any values above this corresponds to unstable profile, because h is more than the Blasier's profile. And that is what you are also noticing, that the same station, if your h is larger, the capital N factor is significantly larger, right. So, you can see that for a Blasier's profile to go unstable, and if I say e to the power 9, you can see it would have to traverse much longer distance. But if you look at 2.68, well, it would indicate that by this time that value n is equal to 9 has reached here, right. So, if you look at 2.8, it is so unstable, right, and as you approach the incipient separation profile, you can see it basically virtually goes up. So, basically then one should be in a position to talk about flow being stable or unstable by looking at the local pressure gradient. So, we are essentially studying the effect of pressure gradient on flow instability, right. That is why we are considering all these flows. Now, what we are seeing here is plot of h versus RE. On the y axis we plot h, the shape factor, on the x axis we plot RE, scaled down by a factor of million, and this discrete data points that you are seeing, those are the corresponding experimental observation. Okay? And this solid line indicates, say, some effort for calculating the boundary layer. We can solve the boundary layer equation, and then we can calculate its H, and then we see what happens. What about this A? A corresponds to a case where we are talking about a 0 pressure gradient boundary layer. So, corresponding to that, the H value remains flat at 2.59. But if I go to the lab and do the experiment, I do not see that remaining flat. It actually fluctuates a little bit and then it drops. Now, what does it signify for the H to drop? Which flow would you expect to have higher H, laminar or turbulent flow? See, what we saw that when we had adverse pressure gradient, H values were larger and the boundary layer was thicker. Now, what happens when you have a turbulent flow? What do you expect to happen? You would have larger wall normal fluctuation. So, there will be more mixing. If you are going to have more mixing, then what will happen? The boundary layer will be somewhat relatively thinner, but at the same time, because of the larger mixing, we are also going to experience larger losses, drag, right? Turbulent flows invariably will have more drag. So, if I now look at the expression for H, is delta star over theta. Now, if I take a flow over, let us say, a flat surface like this, then what do I see in an experiment? I have a laminar flow profile, then flow becomes turbulent and then goes like this. So, what you are noticing that delta star increases also for the turbulent flow, because you are giving now a v velocity fluctuation. So, of course, shear layer would appear thicker, but what is happening, the corresponding growth on theta is much larger than the growth in delta star. So, the two together actually conspires to give you a value of H which is much lower for turbulent flow as compared to laminar flow. So, whenever you see such a thing happening, that H falls off, that is an indication of transition. So, we are talking about a physical understanding of features of the mean flow, the equilibrium flow, that helps us identify what is going on in the flow. We do not need to really do those detailed stability calculations to even comment upon things, but if I do plot let us say experimentally H versus RE, and if I see that this is falling off, this indicates there is a sort of a gradual transition that has taken place. So, that the value of H has fallen from 2.59 to somewhere in between 1.3, 1.5 in that range, right. Now, that was your 0 pressure gradient scenario. Now, let us look at adverse pressure gradient scenario. Now, what will happen? You see, if you do a boundary layer calculation, what you would find, because it is adverse pressure gradient, the H increases as we indicated, and in fact, you would notice that after some distance, you would have this criteria satisfied. So, you would have a flow separation that is indicated by this vertical barrier. So, that your boundary layer calculation cannot go beyond this. What happens to the experimentally observed shape factor? That you can see that it falls off. So, while this is a theoretical laminar flow, but actual flow undergoes transition earlier and that is what you are noticing here. Now, make the pressure gradient even more stronger, then you would see that your laminar flow calculation will break down earlier. However, you would also notice the transition would have occurred even earlier than that. What you notice that further increase of the adverse pressure gradient brings a situation where the point of separation and point of transition becomes virtually the same, like the case E and F. Right. So, basically then gives you an understanding that looking at the boundary layer diagnostics itself, you can talk about what is really happening. What you actually the difference between the place where the flow separates and where the transition occurs progressively becomes smaller and smaller with the strength of the adverse pressure gradient. So, if you have sufficiently strong adverse pressure gradient, you do not need to do many fancy calculations. You can very safely say the point of separation and point of transition are synonymous, they are same. Okay. Now, you also notice one interesting thing is this fall of H is rather instantaneous here with a larger adverse pressure gradient, whereas for milder adverse pressure gradient, what you notice the transition is rather gradual. It just does not happen instantaneously like what you see on this right hand side frames. So, do understand that this is both a sort of information as well as a message of warning for us how we should look at flow past bodies where we would like to control transition. For example, if I look at flow past this aerofoil, then what happens? Well, if I look at 0 angle of attack case, what we would expect to happen? Well, we will expect to see the following scenario. We will expect to see the following scenario that flow will approach the aerofoil and there would be some kind of a stagnation point here. Then if you follow the flow on the top surface and the bottom surface, you are going to see some qualitative difference. But what will happen? If I look at another nearby streamline, it will go like this, right. So, what does it mean here? In the early part of the flow, this is where of course stagnation point means flow has stagnated there, and then the flow actually start accelerating from there, and the acceleration will go on till the position of the maximum thickness. Beyond the position of the maximum thickness, what happens? The streamlines diverge. So, that means the flow experiences adverse pressure gradient, right. So, you would see that in real flows like what one may be interested, you would get an admixture of all. Okay. And this is what you are going to expect. What you are going to expect that at least up to the maximum thickness point, flow is accelerating. So, if there are any background disturbances, they will be reduced. That is what we have seen, that the accelerated flows are more stable than decelerated flows. However, beyond the position of the maximum thickness point, flow will experience more and more adverse pressure gradient, and this is where you can draw inferences from this kind of study, right. So, you can see that in a profile like this, it is virtually impossible to keep the flow laminar indefinitely. what happens is, this was known to people, experimentalists, that maximum thickness value and the location determines the property, sectional property of this kind of aerofoils. This prompted those people at NACA, National Advisory Committee of Aeronautics. They designed a series of aerofoils which are called NACA 6-digit series aerofoils. Which benefited from this observation that you have to postpone the maximum thickness point. That is what you should look at any aerofoil data book, and you would notice that how the maximum thickness and the position of maximum thickness point has changed during that period. This 6-digit series aerofoils, they try to push the maximum thickness point as far back as possible. In fact, those pictures that we saw of Honda Jet, which I said uses natural laminar flow aerofoil, they also there also you would notice that the maximum thickness point is location, whereas this 6-digit series are a little earlier. Now, this is all there is to your common sense applied to the understanding of the flow. We will talk about this as we go along, but you can see that in actual flow it will virtually be impossible to keep the flow laminar over the full extent of the body, right. So, this is something that we must keep in mind. Okay. Let us now talk about other effects. We have now just talked about effect of pressure gradient, right. What else can affect transition? Well, of course, the main thing is going to be the background disturbances, right. Here what we have done is what we just now discussed. We have plotted RE, Reynolds number, versus the shape factor, and there are collections of data, those have been plotted here. This is the first line corresponds to your where the flow becomes critical. Okay. For different values of h, it happens at a different location, whereas the second curve corresponds to where the flow becomes turbulent. So, what you really need to understand, instability does not necessarily mean transition. As we saw in the previous frame also, if you recall, we did talk about it, that if our value of pressure gradient is not too adverse, then there is a distinction between where the flow becomes unstable. Where the flow becomes unstable, h has the tendency to fall, but it reaches that turbulent value much further down, right, much further down. So, there is this difference between the point of instability and point of transition, that this thing sort of disappears with adverse pressure gradient, and that is what this nice figure is. This is a compilation of data from various flows taken from White's book. What you notice that this is the locus of point of instability and this is the locus of point of transition as predicted by e to the power 9 theory. You see, we did talk about the total amplification rate. When this is about 9, then where does it happen? So, this is this. So, depending on the value of h, if h h is smaller, then you can see that this critical and the I x calculated from e to the power 9, they kind of comes closer, but they seem to open out. What does it imply actually? This is just the opposite to what we have been talking about. This basically tells you the limitation of e to the power 9 theory, right. E to the power 9 theory may say that okay, for larger value of h, which means the decelerated flow, there would be a significant difference, but that does not happen so. So, please do understand that this linear theories do have their limitations. Okay, that is what we are talking about, limitations of linear stability theory. This envelope method that we did talk about, e to the power n method, does not require any information about the frequency content, or that is what we are calling about the spectrum of the disturbance. We just somehow say that it is a mishmash of the whole thing. Whenever it reaches the value of n equal to 9, we are done. And it also predicts transition based on higher frequency events. But suppose I talk about a disturbance environment which do not have this kind of components, then what do we see? So, basically we are talking about nothing but the background disturbance environment that is going to play a significant role, right. This is what Reynolds did in the early part of the development of the subject. He used to, I told you, come past midnight doing those experiments, and he used to use that bell mouth to control the input disturbances, but the linear theory does not really give you any room to put in there directly, although of course one can always, if you know a fact, you can always create some kind of a empirical correlation and you can put it in. What we need to really talk about then is basically the background disturbances, right. In addition, linear theory may not be everything. What we may need to know is basically a nonlinear theory, okay? Because we can see the growth, the spectrum, all this thing depends upon the amplitude of the disturbance. Higher the amplitude, we may actually see a growth which will depart significantly from what the linear theory predicts. Okay. And we have also seen that this linear theory, the way it was developed, it did not talk about where the disturbance originated, whether the disturbance was applied from inside the shear layer or outside the shear layer, did not. Because how we got the eigenvalue formulation? We gave those disturbance values to be equal to 0 at y equal to 0 and y going to infinity. That is one of the serious theoretical drawback of all eigenvalue theories. However, those experiments by Schubauer and Skramstad specifically reported that they could validate the linear theory only when they created a disturbance inside the shear layer. But suppose you are flying an aircraft, of course, the wing surface vibrates because of structural vibration that can create a seed of disturbances from inside. What is the other possibility? The possibility would be the background disturbances are with the oncoming flow. Those disturbances are what are called as free stream turbulence. So, the free stream, what we are always used to taking as u equal to u infinity etcetera, they are hardly ever so. There will be always disturbances riding with the uniform flow. And all this theory seems to work if this level of free stream turbulence is low, then of course, you are free to ask the question, what happens if the free stream turbulence is low. Okay, so, we are asking a very legitimate question that if free stream turbulence level is higher, will our linear theory work? That is a very neat question to ask, or even the mechanism by which we have talked about this disturbances grow is through the viscous mechanism. Will that mechanism follow the same route when the amplitude increases? This exercised the mind of many researchers. One of the best mind in the field was Markovin. He did study this problem very intensely, and he noticed that this linear theory works for shear driven flow like a boundary layer to some extent. But if you look at internal flows like flow inside a pipe or the Couette flow, you know the Couette flow is if you have a fixed plate and have another moving plate, the flow is completely shear driven. There linear theory says flow is stable, even using the viscous flow analysis. Then if you talk about flow inside a channel which is called the Poisson flow. In the Poisson flow, the linear theory predicts a RE critical which is close to 5770. Okay. However, people have done experiments and they have seen that channel flows can be destabilized at a lower Reynolds number of something like 1000 or so. So, these are the early indications that linear theory is okay for external flow, shear driven flow like of a problem of this kind of engineering interest, and it did do a lot of good work. However, if the disturbances are not low, then you may get a mechanism of transition which does not create those instability waves, which we call as the Tolman-Schlichting waves. It will completely bypass that route, and those transitions are what are called as bypass transition. So, we will spend talking about some of those bypass transition mechanism. Then of course, there could be nonlinear effects. Nonlinear effects could be significant, and to that we will add a third element. This is rather very important, which was not greatly appreciated even a couple of decades ago. Although people have talked about transient growth through mathematical subtleties of talking about non-normal modes, etc., but in some of our work we did show that when we look at even stable boundary layer, there is a possibility at the onset of disturbance you could get a very large spatiotemporal wave front, spatiotemporally growing wave front. This was postulated by Brillouin in the context of electromagnetic wave propagation, but never very successfully it was detected. Fortunately enough, that when we started looking at this problem ourselves, and we looked at it from a not a stability perspective, but from a receptivity perspective, if we create a localized disturbance and the flow is say stable from the spatial theory, we still can create this maximum growing disturbance. A good analogy would be for it is like what you may actually see in a tsunami. You would get only 2-3 peaks and valleys, and it grows very rapidly as it goes downstream. We will talk about this, and this we are going to cover in this course. Okay. So, now one of the things that characterizes the disturbance level is, as I told you, is called the free stream turbulence. How do you define free stream turbulence? Well, there is an age old definition of turbulent intensity Tu, which is nothing but u prime square, v prime square, w prime square divided by 3. So, that is a kind of average mean square fluctuation, then you take a square root. So, it is a root mean square fluctuation scaled by the oncoming flow velocity. That is how we define the turbulent intensity. In this respect also, I would like to sound a word of caution that despite what all the experimentalists trade data among themselves by saying, oh, I have a tunnel of turbulent intensity of this value and that value, please be aware. Please be aware, they may not know what they are talking about, because the turbulent intensity is also a function of the oncoming flow velocity, right. So, it is quite unusual that people have depended so long to try to define a phenomena of turbulence which is essentially stochastic in terms of a single moment. What is this moment? This is the second moment, right, RMS value. What happens to other quantities? Of course, the mean is taken care of, that is what you calculate. Second moment is okay. What about the higher moments? This we will talk about and we will see and will show that it is very, very significant that you should not lose sight of this. And also the fact that this is not something that you can just simply talk about one. We will show you some experimental result, experiments done in the same tunnel. So, from experimental perspective has the same TU so called, because that is what they always try to quote you a single number. But in the same tunnel we did experiment with flow past a cylinder of 2 different diameters. So, to keep the Reynolds number same, what we had to do for different diameter, we had to change the speed, and what we saw is a totally different footprint of transition. We will come to that. Nonetheless, historically people have gone through it, and let us show you what we get. This is a plot of transition Reynolds number versus turbulence intensity. Okay. And this solid line is the classical experiment of Schubauer and Skramstad, which shows that as turbulent intensity increases, that RE transition comes down. But please do note that in their experiment, they did not see effect of turbulent intensity below a level of 0.1%. So, there has been a kind of a myth gone around, which says that if your turbulent intensity is less than 0.05 or so, you have extremely low turbulent intensity tunnel, and that is quite okay. However, if I am seeing a fluctuation, this is what? Any disturbance in a fluid flow can be classified into few generic components. One of the component would be the vortical disturbances. I can create small eddies. Those could give rise to this u prime, v prime, w prime, right. That is your vortical disturbance. However, I could also create an acoustic disturbance, noise, acoustic noise. Are these two things same? Common sense tells us no. But unfortunately, when you talk about TU, this TU does not tell you that this TU has been calculated is based on the vertical disturbance or acoustic disturbance. So, people do actually try to rationalize, saying that this insensitive path at the lower level, this is due to acoustic disturbance. I mean, those kind of disturbances, turbulent intensity, are due to acoustics and they do not affect. It is only when it becomes vertical they start affecting the transition location. Here we are seeing some results which were reported by various people. The acoustical disturbances were created in a wind tunnel experiment for flow past a flat plate and these are different frequencies 27, 43, 76, 82, and this is one case where some grids were put in the beginning of the test section. This grid data is this one, and this grid data tells you a very, very good story here. What does grid create? Vertical disturbances, eddies directly, and the moment you do that, you can see that it actually brings down the transition location very, very upfront. That is what it is, right. So, if I create a particular grid of this particular experiment, this was the curve. Now, we are seeing lots of other interesting data, that this is what is for acoustic disturbance of frequency 76 hertz, right, 76 hertz, and this is for 82 hertz, and those two sets of data are here. So, why did Schubaugh and Kramstad fail in creating instability and transition by acoustic excitation, while this data shows there is some dependence? Well, please do understand that Schubaugh experiment's main aim was to validate linear theory. The linear theory, what were we studying? We are studying a two-dimensional mean flow with two-dimensional disturbance field. Acoustic disturbances, can it be 2D? So, you can understand that you will have to study the flow from the perspective of three-dimensional disturbances, and we cannot use the square theorem, that is what we have said. For a three-dimensional flow, if you are looking at spatial instability, square theorem does not work. You will really have to study a three-dimensional. Despite that, this result seems somewhat perplexing, that while some frequencies you see dependence on the turbulent intensity, whereas for this case it remains flat. Why is that so? If I create acoustic frequency of a particular frequency, where is it that I am getting different value of Tu from? It is not due to acoustics. Acoustics is a fixed frequency, or is it that they have increased the amplitude of acoustic excitation and by that they are controlling Tu? Or if I create a very large amplitude acoustic disturbance, first it creates a vertical disturbance and that in turn destabilizes. There are so many unanswered questions in this area. So, this is something that you should keep in mind, and there is some results which also talked about basically where you created a kind of a standing wave. See what happens if I am doing an experiment in a wind tunnel. So, it is a closed section wind tunnel and I put a model inside, then the waves, if I create acoustics, that will continually reflect from top and bottom, and depending on the condition I can also create a standing wave, and that is what one of the results are. Say this one, this data is due to Wells, which says that there was a grid, but in addition there were some standing waves noted. Okay, so, this tells us that we need to do something different from linear stability theory, and I basically am drawing your attention to what is known as the receptivity analysis. In receptivity analysis of the shear layer, what we need to do is we relate the cause and effect. Okay? So, that means what? You are talking about the background disturbances, etc. Whatever is the source of excitation, you try to find out. And you can see what Schubar and Skramstad noted themselves, that in the search for schemes to excite oscillations inside the boundary layer, they did try a number of devices before they completely obtained satisfactory result. What they noted, that methods using sound, both pure notes as well as random notes, were not satisfactory because of some kind of resonance effect, and those also created complex wave patterns. And I told you that their experiment was geared towards validating a 2D instability, while acoustic excitations are always 3D. And you would agree with me, there is absolutely no scope of creating 2D acoustic excitation, absolutely no. Then this part we need to keep in mind that in eigenvalue analysis, the excitation field information is completely lost because of our insistence upon satisfying homogeneous condition. It is even worse if the excitation is applied in the interior, there are no theories of instability. So, we always create disturbances on the boundary. Suppose I put a sort of a vibrator somewhere in between, instability theory, eigenvalue theory, that has no clue, can't say what is going on. So, it was the situation till the mid 80s or so. Then some of us tried to rectify the situation. Then what we tried to figure out, that when we retain only two modes in linear stability theory, we are actually considering excitation at the boundary y equal to 0, which decays with y. So, that is what we call as the wall mode. Okay. So, we will start from here in the next class, and we will see how we can systematically develop a theory of receptivity and find out lot more meaningful information than what is given out by the eigenvalue theory. Okay.